Got it? I will begin with a word of prayer. It's almost time to start class. Sorry, I'm starting early. You'll forgive me. Dear Father, we thank you for this day. I thank you for these students and for the weekend that's about to start. Just help us to make the most of this time, Lord. In your name I pray. Amen. So there has been some discussion about the help session for abstract being directly after this class versus after this class. No? See, there's apparently two camps. I need to take a more concerted vote after class, not right now. Do it on Thursday. All right, so let me remind you, what is Dn? The dihedral group, Dn, was, what was it? It was equal to, in generators and relations, we could say it's generated by A and B, such that the order of A is n, the order of B is 2, and the fundamental relation is that, how's it go? B is equal to A inverse. I said that defines, meant to put a wrangle here, defines the dihedral group. It's actually of order 2n because it's got 2n things in it. So this is just a slick notation for 1 a squared, a to the n minus 1, b, ba squared, b a to the n minus 1. And so if you count there's 2n things, right? So the order of dn is 2n. All right. Anyway, one of the things I claimed last class and didn't quite do justice to was that the order of b a to the power j for any j is in fact equal to 2. This is a claim. So let's prove that claim. All right. I'll prove it I will attempt to prove this in an orderly fashion. And to be more clear, this is for all j in, the natural numbers and also 0. All right, so first order of business, how about, to start with, it's given, right? b a to the 0 is equal to b, and we know that the order of b is equal to 2 by assumption, right? So it's true for j equals to 0. How about j equals to 1? Let's see here. So consider that ba squared, right, is equal to baba. All right, but what is baba? It is A inverse A, actually. See, because this bab is A inverse by construction of the dihedral group. And so A inverse A is E, right? I'm sorry, I'm trying to use 1 at the moment. I forget what my custom has been throughout the notes. It may be 1, it may be E. I can't remember right now, folks. I'm sorry. Okay. Long story short, I won't count you wrong if you use either one of those. Or maybe even if you use both, as long as it's not in a crazy way. Okay. Now, what does that say? That says that the order of ba squared is at most 2. How do I know it's not 1? How do I know that the order, this implies that the order of ba is at most 2. What would it mean for the order of ba to be 1 then? What would that say? If the order of ba is equal to 1, then ba is equal to 1, right? That's what that means. It is the identity. Is b times a the identity? It is not, right? This would say that b is equal to a inverse, right? And that would say that the order of b is equal to the order of a inverse, but we proved that the order of the inverse is the order of the element, so we know that the order of b is given to be 2, right? And we know that the order of A is given to the n, and n is not equal to 2. I guess I should be assuming something, right? I forgot to tell you the context here. For a, b, in dn, n greater than or equal to, n greater or equal to 3. I guess you could talk about D2. I don't know. What would D2 be? I don't know what D2 is. D2 is weird. Yeah.
I don't have input on that. I have a quick question about what you just said.
Yeah.
By what rule do we know that if B is equal to A inverse, then they're of the same order?
If they're the same element has the same order.
But is an inverse necessary? But if B is equal
When I write B equals to A inverse, that means B and A inverse are the same element.
Right. So how do we know?
How could the same element have different orders? I mean, order is well defined.
Oh, right.
Okay. It's fine. It's good to question things. Right?
Okay, so
Okay,
maybe my question is, does an element and its own inverse have the same order necessarily?
It's an element. Yes. Yes, we prove that.
That is what
That we have proved, yes. It is indeed good to know, and it is true. All right, so, and also a good test question, given that the order of A is n, prove that the order of A inverse is also n. A fine test question indeed, now that you mention it. Thanks for that. So, I'm not trying to strike an adversarial pose towards questions. That's not my point. I'm just messing with you. All right, so great. It's true for j equals to 0. It's true for j equals to 1. Let's proceed by induction, right? Suppose, on j, of course, suppose that the order of BA, let's say BA to the n. Oh, I can't use n here. It has a separate and fixed meaning. Oh, so let's suppose BA to the j, the order of that is equal to, goodness, 2, obviously. Idiot. Me, not you. Suppose that the order of BA to the j is 2. And we'd like to consider, BA, j, right? B, I'll get it eventually, folks, here. B times A to the j plus 1. By definition, and we want to look at the square of that, right? What's that? It's Baja plus 1. Baja plus 1. Like that. All right, well, what's that? What can we do here? Looks like we have BA to the power j, BA to the power j, BA, right? By laws of exponents. What can I do with the middle pair? By the induction hypothesis, that's what? That's 1, right? Because we're assuming that the order of BA to the j is 2, which means that it squares to the identity. So by the induction hypothesis, the middle pair, this just goes to 1. By the induction hypothesis, which I will underline right about here, right? And so you got BA times BA, which is what? That's BA squared. We proved the, yes?
How did you go from 2b's to 4?
2b's to 4. You tell me. And this is equal to 1. Notice the distinction? So like this one, look, this is the j plus 1 power, right? So I have, oh. Oh, I see your point. It looks so nice. But it's based upon a rather unfortunate fallacy, which is that BA to the J plus 1 is not equal to BA to the J plus 1. Curse you, English. Right? I mean, this and that these are not the same thing, which is what I just talked myself into. This is the danger of verbalizing math. Don't verbalize math. All right, let's try this again. The starting step is not wrong, I think, right? Yes. And this is B, A to the J, B, A to the J, A. I don't know if that helps or not, but there you go. Maybe, but I can point out something. I mean, I need a side calculation here. We know that BA to the J times BA to the J is equal to what? By assumption, by the induction hypothesis, that's equal to 1, right? And let's see here. So that means that implies that A to the J, B, A to the J is equal to B. If I just multiply by B. Do you guys see that? Multiply by B, we get B squared, which is 1. So A to the J, B, A to the J is equal to B. Now that is super nice because that means this right here is in fact B by the induction hypothesis. And that little bit right there. So what we got is we got BA, BA, otherwise known as Baba, otherwise known as 1. Now this is not the end of the proof. What do we have shown now? What have we shown? Thus, the order of B, A to the J plus 1 is less than or equal to 2, yeah? Because we show that squares to 2. We still need to argue what? It's not 1, right? So what would it mean if it was 1? If the order of this was 1, that would give us that BA to the J plus 1 is equal to the identity, which then would imply what? Multiply both sides by B. Right? Yep.
Should AJ times B times AJ equal to B inverse?
What is B inverse? So we got B, B, A to the J, B, A to the J equal to B, yeah? See, BB is 1. You're not wrong. It's just that B inverse is equal to B. That's all. So if that's equal to 1, that means that B is equal to A to the J plus 1, right? And at this point, I need a result from later in the cyclic group lecture. Actually, to understand the order. I mean, what is A to the J plus 1? All right, it has an order which has to be a divisor of n. It turns, I mean, this is, so unfortunately at this point I actually need, I think I need a result. This is a claim from the future. The order of A to the J plus 1 is a divisor of n, right? So I suppose that, man, that could be 2, couldn't it? I must admit I'm stuck at the moment coming up with a contradiction why the order can't be 1. Can somebody tell me a good reason why the order can't be 1 here? Order is not helping me at the moment. I can't see my way through the order contradiction. Yeah?
Why does it not work to do the same thing as before? Like to say that that would imply the order of a to the j plus 1 is 2.
Why is that wrong? Why couldn't the order of a to the j plus 1 be 2? You know, if I'm working in D3 and j is equal to, if I'm working in D4 and j is equal to 3, j is equal to 2, j is equal to, I'll get it eventually, j is equal to 1, then a to the 1 plus 1 is a to the 2, and you know what? A to the 2 is a to the 4, which is 1, so you know what? The order of a squared is equal to 2. The order of a squared is equal to 2 in D4. So that doesn't give me a contradiction. You see, I'm in trouble using order to get the contradiction for the general case. We got to get the contradiction somewhere else. We need to prove that a to the j plus 1 times b is not the identity, some other way. What else could we pick at to get a contradiction other than just order? I mean, it's not working. How about the other relation, right? So we're supposed to have that b is equal to a inverse, right? So we ought to be able to get a contradiction from using that. So hit this. So b a to the j. So b a to the j plus 1 is equal to b a times a to the j, which is equal to 1, right? And then what I'm going to do is I'm going to stick in a copy of, I'm not sure this is going to help or not, I'm just trying something, guys. BB, like that. So I'm going to have, like, you know, I can do that because it's identity. So I get b a to the j equals to a inverse, right? These steps are reversible, right, by the way? But what is BAB? And this is a reversible step, right? This and here, again, is a reversible. These are if and only if, yeah. What's that? Yeah, this is A inverse. I don't know if that actually helps or not. I'm just trying something, guys. Oh, that's kind of neat. So we just got A inverse BA to the J equals to A inverse. So then we can multiply both sides by A. What's that give us? Which is to say, if and only if the order of BA to the J is what? And that contradicts the induction hypothesis. Yay, contradiction. Therefore, the order of BA to the J plus 1 is 2. Sorry I spent so much class time on this, but I think it's a worthwhile exercise for all of us to go through. Yeah? Yep.
I see you stuck a green marker there where it says
Ah.
A inverse on the right side. Where did that come from?
This here?
No, one to the left. That one. Your right most case.
Right.
Because I see you put in the BB and change BAB to A inverse, but why did the right side turn into A inverse as a 1?
Oh man, did I just cheat us? Ah. Well, it was a nice contradiction. Well.
Wouldn't it still work because then you would just have b times a to the j minus 1?
I think we're still going to get a, yes. So we have, you're right, Stephen's right though, that's 1, which makes this not A but A inverse, which, well, Pox upon you, Stephen. Let's see here. I mean, thank you. That's great. Very helpful. It's better to know our error in class than find out afterward. Yes?
So A should still be 1, and the one to the right of the green expression with the brown one. The expression to the right of the green expression with the brown one should be equal to 1 instead of A.
This?
And then the next equation will have
Oh.
A to J is equal to A.
Oh, okay. Oh, and right, then we get that this has order n, which is not equal to 2. So there's your contradiction. Thank you. Well, the order of A is n. So if this is equal to this, the order of BA to the J is the order of A, but the order of A is n. That's given. But the order of BA to the J is, by the induction hypothesis, 2. Contradiction. All right. Whew. I was worried for a second there. Let us go on, if you guys don't mind. So next, in your homework, I have asked you something about, they're like elephants or hoodlums, rugby team upstairs. I mean, what's going on? What's that? We're on the 4th floor. Yeah. Yeah, I mean, they're on the roof. Is the soccer team practicing up there? I mean, I don't know what it is. It's it's a dance group. I don't know. That's not very rhythmic. Maybe Krav Maga. I can envision something being like thrown or Taekwondo perhaps, right? Not a Bushido though. Sounds wrong. Anyway, sorry. So, definition. If G1 with, let's say, star 1 and G2 with star 2 are groups, then G1 cross G2, which of course you guys should know is the set of G1, G2, such that G1 is in G1 and G2 is in G2. Shame for me writing this down, but I'm just defining for you guys, of course, the Cartesian product of G1 and G2. Then the Cartesian product G1 and G2 is itself a group. A group with respect to the operation star defined below. Here it goes. X1, well, let's say, yeah, fine. X1, X2 times Y1, Y2 is by definition X1 star 1, Y1, comma, X2 star 2, Y2. So this is the so-called direct product of G1 and G2. And we can prove that the star that I just wrote down there, in fact, defines a group on the Cartesian product. Let's go through that. First of all, is it a binary operation? And to make things a little bit easier, let's give this thing a name. Let's call it G, right? So is star a binary operation? Does it take in pairs from G cross G and map them to G again? So look at it. You know, if I have, X1, X2, Y1, Y2 in G, does that imply that this is in G? You know, is this in G? Why is it in G? What does it mean to be in G? It means that the first component's from G1 and the second component's from G2, right? So how do I know that X1 multiplication 1 times y1 is in G1. Well, that's because G1 is a group and star is its multiplication. Star 1 is its multiplication. So the fact that star is binary follows from the fact that star 1 and star 2 are binary operations on G1 and G2 respective. Okay? Associativity. I don't want to write down. Fine, I'll write it down. You guys tell me. All right, here we go. Let's get nuts. X, I'm gonna make up some letters. X, Y, A, B, C, D. That sounds, you know, I was keeping it professional around here. Let's see here. It's good. Let's see here. So So to associativity. Let's look at that, right? What do we got? Oh, dang it. I regret using star 1 and star 2 at this point, but it's too late. I'm too far in. If I was smarter, I would have used juxtaposition. But again, it's too late. So we're stuck with these stars. So star 1 for the first component, star 2 for the second component, and then to operate again, we get x star 1 parentheses a star 1 c close parentheses comma y star 2 parentheses b star 2 d close parentheses close bracket. And then what do? To move the parentheses, we use the associativity of the groups G1 and G2 separately, right? So this is equal to x times 1a parentheses times 1c comma y star 2b parentheses star 2d close parentheses by the, this is going by associativity of G1 and G2. And then we undo the multiplication, right? This is nothing more than x star 1a comma y star 1, star 2 rather, star 2b times in the group c comma d, which then of course is bracket x comma y star a comma b close square bracket star c comma d, which is associativity of the alleged group operation on the Cartesian product, right? So there you go. Associativity of the components transfers to associativity of the direct product. What is left? We got binary, we got associativity, we need to check inverses, we need to check identity. What's the inverse? Yeah. What would xy inverse be? It's actually going to be x inverse, y inverse. You can check that. Also, the identity, if you will let me EG, guess what? It's going to be E1, E2, where E1 is identity for G1 and E2 is identity for G2. And you can prove that that does in fact serve as the identity. All right? So you have a question in your homework where you're supposed to prove that H1 cross H2 is a subgroup of G1 cross G2. I now have given you license to assume that G1 cross G2 is a group, and this is its operation. So you can go from there. Now you just got to show that your homework problem is to show that, H1 subgroup of G1, H2 subgroup of G2 implies the Cartesian product of H1 and H2 is in fact a subgroup of G1 cross G2. So what I've just described for you is the group structure on this. Now you can make sense of that homework problem, okay? It's actually not that bad a problem, but the notation's different, right? Instead of having star 1 and star 2, I gave you like diamond and a wedge, right? I don't think I even gave you a notation for the product on the direct product, like the actual notation for the multiplication on the direct product, so you can make it whatever you want, you know? All right, well, enough about that. We'll come back to the direct product as we go on. It appears in my notes a little bit later. I'm sorry I didn't. It's an oversight on my part. I meant to introduce this earlier. As you can see, I now have completely messed up the sequencing of this lecture, being that we have 20 minutes left. So let's see here. I have no regrets. Everything we did today are things we should have done anyway, so, you know. I won't tell anybody if you don't tell anybody that I didn't exactly follow my course planner. Is my secret safe with you guys? Okay. We should be pretty much back on track by the end of Monday, though. See, the lecture 6 and lecture 7 are really on the same topic, which is cyclic groups. It's just lecture 6, I pretty much made the calculational core of the cyclic group discussion, whereas lecture 7 is applying that to the study of subgroups. So let's get to it. Actually, first order of business is just a reminder about what cyclic group is defined to be. This is important. If a group G, right, is equal to Langle-Rangle A, Langle-A-Rangle, if it's generated by A for some A in G, then G is cyclic group with generator. I will remind you that A either means A to the n, such that n is in Z, right? Or this means NA, such that n is in Z, depending on what. How do you know which it means? Yeah.
Whether you're in a group with that's under addition or multiplication.
Right. It depends on if we're using an additive group or a multiplicative group. The top is for a multiplicative, and the bottom is for an additive. So the additive group, the identity is 0. In a multiplicative group, we typically use identity E or sometimes 1. All right. If you look at stuff from last year, the book I was using last year used 1 for E, right? Which has the effect of making students feel more comfortable than they ought to be, is what I saw. Which maybe is a good thing, I don't know. So we all need to live lives of delusion at certain points. Let's see here. 1 r squared f. I mean, do you really want to know what reality is? Let's see here, f. I mean, the ultimate reality is that Christ already won the battle 2,000 years ago. But man, if you look around, it's easy to think otherwise. I don't know. You know what I mean? Like the day-by-day, what people are doing, direction society, evildoers not being punished, stuff like that. Let's see here. Now, have I, F, RF, I don't know what I'm talking about. There's no evildoers. Everyone's great. Everyone's fine. I'd say we can agree to disagree, but we don't agree. We don't believe in agreeing to disagree. We believe in people agreeing. And if you don't agree, But I think that the way I've done this is probably more honest for me to put it like this. That's more in the spirit of 1a, a squared, b, ba, ba squared, right? That was the formatting I was using, so I think I have the opposite in the notes. But anyway, question, what's the order? What is the cyclic? If you look at the cyclic subgroup generated by 1, you get 1. If you look at the cyclic subgroup generated by r, you get 1 r squared. If we look at the cyclic subgroup generated by r squared, we get r squared r and 1 also. If we look at the cyclic subgroup generated by f, we get 1 and f. If we look at the cyclic subgroup generated by FR, we get 1 and FR. If we look at the cyclic subgroup generated by FR squared, we get 1 FR squared. So here is all possible cyclic subgroups generated by all 6 elements of D3. Are any of them all of D3? No, they are not. Therefore, by brute force or fast talking, whichever you prefer, this shows you it's in your face, D3, not cyclic. Okay, there. So there's an example of a group which is not cyclic. There are lots of them, yes.
Does the order of the things in the set matter?
Nah.
You just switched one of them. One of them went the opposite direction. The R squared was the only one he went the other way.
Yeah,
Okay.
just to keep you guessing. I mean, they're sets. They're not ordered.
Yeah.
Except when they're a basis, and then they are. Anyway. All right. Moving along. Here we go. Go for it.
Is the first one the set of one?
Oh, yes. Thank you. Yeah, I would have taken off like half credit on your test for that. Let's see here. Thank you. Good point. If you look at the cyclic subgroup generated by 1, and 1 is actually the number 1 as in the integer 1, it's an additive group. So this would be like, n times 1 such that n is an integer, also known as, I don't know, the integers. So the integers are a cyclic group under addition with the generator of 1. Is there any other generator of the integers? What else could you repeatedly add or subtract to generate all integers? What's that? Fill in the langle-wrangle. Yes, -1. You are correct. Yes. Them's your choices. Anything else is not going to do it, right? If you use 2, you just get evens. If you use 3, you get the... What are those called? Yeah, those are right, the Larry numbers. Thank you. Very good. Yes. Yes, we've decided that 3z is Larry, that 3z plus 1 is Mo, and that 3z plus 2 are curly numbers. How do you spell curly? I don't know. Curly? I don't know. But it's not especially important. So in Z4, if we look at 1 or 3, we get Z4 back again. If you look at the cyclic subgroup generated by 0, it's just 0 again. And if you look at the cyclic subgroup generated by 2, you get 2 and 0. Or you could start with 0 if you like. I mean, 0, 2. The point is that's it, right? Because 2 plus 2 is 0, which, order 2. So those are the cyclic subgroups generated by various elements of Z4. There are 2 elements, two things in Z4 that generate it. Another example, Z7, 1, 2, 3, 0, 1, 2, 3, 4, 5, 6, and 7. Oh, no 7, right? That's 0. Already got that at the start of the list. If you look at this one, and by the way, what is 3 as it relates to 1? 3 is -1 in the previous example, right? So it's not so different than the integer example. I mean, going forward, it's pretty obvious that we can always use 1 as a generator of Zn additively. And also, n minus 1, most likely. What is it?
Oh, sorry. I guess we were just wondering.
Remind
We
me.
don't
Understand
have to
how you're
define
solving
the, like for 1, 0, 2.
So why does the wrangle 2 equal the set of 2 and 0? Where are the...
So if I take 2, right, and I look at 1 times 2, and then 2 times 2, and then 3 times 2, well, I get 2, I get 0, I get 6, which is 2, and so forth and so on down the line. So this whole infinite set is just 2 and 0. Those are the only numbers I can get from repeatedly adding 2 to itself. You could always start with the identity. Eventually, you're going to get back there. Well, and if you don't, I should really always start with the identity, not because we're going to get back there, but because, you know, n equals to 0 is part of the definition, right? N equals to 0 is something in here, which always, that gives me either 1 or 0, depending on which context I'm in. Now, Z7, we could generate from 1, and we could also generate from 6, I think, right? I mean, if you don't believe me, we start with 6. We'll start with 0, 6. What's 12? 12 is 5. 5 plus 6? Wait a minute, 5 plus 6 is 11, which is 4. Thank you, you're right. What's 4 plus 6? 4 plus 6 is 10, which is 3. Yeah. What's 3 plus 6? Is 9, which is 2. What is 2 plus 6? It's 8, which is 1 mod 7, yeah. What's 1 plus 6? Anyway, we're back to here, yeah. There you go. So 1 generates Z7, 6 generates Z7, yeah? Okay, it's fine. Do you guys think of anything else that generates Z7? 2? 0, 2, 4, 6, 8, which is 1, and then 3, 5. What do you know? There you go. 2 also generates Z7. In fact, you can keep doing this. Every non-zero element of Z7 is a generator. It's no, I mean, 1 works, 6 works, 3 works, 4 works, 5 works, 2 works. Everything works except for what? Yeah, the cyclic subgroup generated by the identity is just the identity, the trivial group. All right, the trivial subgroup, rather. Another example. Z10. Z10 is generated, of course, by 1. It's also generated by -1, right? Which is what? -1 is 9 in Z, yes.
When you have a 1 in that set, is that meaning the identity like 0? But like, can you write the identity as 1?
Oh, that's just a horrible typo. That of course is 0. No, that's 0. That's just wrong what I had written. These are all additive. These are additive, all additive so far. I'm trying to see if we can see a pattern in what is useful as a generator for Zn, right? The pattern should pretty much start to emerge after I tell you what generates Z10. For Z10, if you look at it, 1 generates, 9 generates. What about 2? We get 0, 2, 4, 6, 8, and oh no, we're back where we started. So 2 is not a generator for Z10. Yeah? What about 3? What happens when you look at the cyclic subgroup generated by 3? 0, 3, 6, 9, 12, which is 2, 5, 8, 11, which is 1, 4, 7, and then we're back to 0. How many is that? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. It worked. Yeah.
Is it like all non-factors including 1?
All non-factors including 1. Non-factors. I think that's probably right. Can somebody think of a different way to say that? Yeah. Right. Exactly. That's exact. So you guys figured it out. Zn is generated by k if and only if the greatest common divisor of k and n is equal to 1. In other words, what are the generators of Zn? Yeah. Right? What do we call those? I mean, what are these such k? Where are all they? They're in a certain multiplicative group, yeah? In other words, if and only if k is an element of un. So any unit of Zn will generate Zn. Let's see here. Can you guys think of any other groups which are not cyclic? So that, I mean, we'd like to prove this, right? I mean, I have not proved that. Yeah? I probably would like to prove it. It's debatable. Let's see here. Example. U10. What are the group of units? 1, 3, 7, and 9, right? So the cyclic subgroup generated by 1 here is actually, no typo. Yeah, good. Great. The cyclic subgroup generated by 3, we got 1, we got 3, we got 9, we've got, 27, which is equal to what? 7. Oh, I guess that's kind of it, right? If you'll allow me this abusive notation, it's sometimes helpful. Yeah? So apparently 3 is a generator. What else is a generator? How about 7? Seven squared is 49, which is 9. 7 times 9 is 63, which is 3. Oh, whole thing again. What about the cyclic what about 9? So you got yourself 1, and you got 9. What happens when we look at 9 squared? We get 81, which is 1 again. That's it. So apparently, the generators for U10 are 3 and 7. How is 3 and 7 related? Well, what's the order of this group, by the way? The order of U10 is 4, right? And if we look at U4, what's in U4? 1 and 3, right? It's not a coincidence that 3 to the third power is equal to 7, and that 7 to the third power is equal to 3. Am I right? In mod 10, what is 3 to the third power? (27), which is 7 mod 10, right? And 7 to the third power is what? 49 times 7, which is what? What's that? Yeah, something ending in a 3. And so when you throw away everything else, you get a 3. Is 343? I wasn't trying to dismiss it. Thank you. And so you see that how was I right though? How did I know that? It's because what we're going to discover is that if you have one generator, so here's one of the theorems that we're going to learn well, hopefully next class I'll prove. Theorem, if G is equal to, if G is generated by A, and the order of G is equal to n, if S is an element of UN, then G is also equal to A to the S. In other words, if you have one generator, you can power it to any power that's present in the group of units for the order of the group. That's why this happened over here. Well, anyway, I'm getting ahead of myself. We'll talk more about that in a future lecture. I guess we're out of time. So, sorry, I've really just gotten to the example part of lecture 6. The theorems are upcoming, and there's a couple kind of important theorems in lecture 6 that I need to go through. So, thanks, guys.